Here's a quick look at the diagram I drew for myself. It's not exactly complicated when drawn out as a diagram. This is the loop test, and I think it's called the Schmidt trigger on the way back. So it normally sits in idle, bouncing the ball from left to right or right to left. Well, let's go left to right. So when it hits the rightmost boundary, the x of the ball is greater than the width of the screen. It enters into this state. This state, the first thing it does is it sends out the reverse signal, and then it just sits there. The next time around, it comes into this state. If x is greater than w, it stays in this state and does nothing. The next time around, when x comes in, if x is less than the width of the screen, less than 800, so let's say it's 750. I'm pulling that number out of thin air, but so if it is, it takes this branch and goes back to being in idle. So it's already sent out the -1 saying go the other way. And now it's come back and it's starting to go, it's gone, ramped up to 800, slightly above 800, back down, back through 800, and then going from right to left until it hits 0. And the same thing happens on the 0 side, here and here. So when it hits less than 0, it comes into here, sends out another reverse signal, and then it just sits here waiting for it to crawl back out of the negative zone back towards the right on the screen. And when it finally gets positive, we take this branch and we go back to idle, the main state of the thing. And the code for that, see if I can, yeah, there we go. The code for that whole class is here. I hand wrote it. And the generated part, so I marked off where I think the diagram would go. And so this tiny little diagram turns into this big glop of Python. And we can see one of the reasons we don't like state machines is that they don't look very good when written out in textual code. But they look fine when drawn out as diagrams. Every state, so the idles, let's look at the idle states. Every state gets 3 things: an entry of the step function and an exit. So to enter idle, we do basically nothing. We just make sure that the state is written as we can write this code in many different ways. This is the way I chose to write it at this time. I probably will optimize it later, but or change it later. But this is where it is right now. When we're in idle, then we check to see if x is less than 0, it's this one here, then we exit from the current state, which in this case does nothing. In more interesting cases, it might actually do something. So exit, and then we enter the next state, which is wait for 0 recrossing. Down here, enter. So we send out the reverse here. That's here. That's that first line. Whoops, no. And what I haven't shown on the diagram, which I need to modify, is that we also send out a loop. Continue on, and then we make sure that the state is correct. So actually, let's maybe change that right now. Send reverse, and loop. And here, send reverse and loop. Okay. And if you go through the rest of this code, you'll see the same pattern emerging. That there's 3 states here. Each one gets an enter, step, and exit. Another state down here. And then the main entry point of the state machine is here, and we check the state, and then we execute the correct step for idle, or for waiting for zero crossing, or waiting. So, whoops, 2 zero crossings. That doesn't look right. W recrossing. What did I call it up here? W recrossing. That should be good. W recrossing. Save it. And that's about. So there's, like I said, there's 3 states. 1, 2, 3, plus the actual driver for the little state machine that executes the correct steps. And we have to make sure that every step it exits itself and enters the next step. And obviously, we could do this with arrays or lists and stuff like that. My guess is that this would be a lot simpler if we just did it in assembler instead of trying to force it to be a bunch of functions. But let's not go there right now.